Good evening, everyone. I am Annwesha. I am a DST Inspired faculty in the School of Computational and Integrative Sciences at JNU. Today, I am going to talk about how you can see fluctuation theorem as a special case of Girsanov theorem. So, to begin with, I'll discuss about give a historical context. So, thermodynamics has evolved quite a lot through the centuries. It started with the classical thermodynamics, where we had the phenomenological laws governing the macroscopic systems in equilibrium. And then the early 20th century, we have statistical mechanics, which gave us the microscopic basis for of thermodynamic quantities and giving probabilistic interpretation of entropy. And currently, the era, which is the stochastic thermodynamics era, where we mainly discuss about fluctuations at small scales, which is very helpful for studying colloids, biomolecules, and active matter, kind of like systems where thermal fluctuations are important. So in this context, we have trajectory level. We introduce trajectory level quantities like heat, work, entropy, and the main tools that we use are Langevin dynamics, master equations, and fluctuation theory. Now, a core challenge in statistical physics is to develop a unified framework for non-equilibrium systems. And stochastic thermodynamics introduces this trajectory level definitions of thermodynamic quantities. Now, on one side, we have fluctuation theorem, which is a very central result, which gives a symmetry relation valid even far from equilibrium. And on the other hand, we have Girsanov theorem, which is a central result in stochastic calculus, which enables measure transformation under drift changes. Now, in this work, we are trying to connect the fluctuation theorem to the Girsanov theorem, which will enable us to use the rich mathematical results which are already present in stochastic calculus to understand thermodynamic behavior in fluctuating systems. Now, what is the Girsanov theorem? It states that if you have two stochastic differential equations with the same diffusion but different drifts, and if you say that one is under measure P and the other is under measure Q, then and we also assume that we are taking an Ito interpretation for all the stochastic integrals, then we can say that the Radon-Nikodym derivative gives that the dq by dp is given by a exponential martingale, and that is it relates the measures q and p of two stochastic processes, where this xi t is related to the change in drift. So, u is basically sigma inverse into the drift change. Now, we have to also take care that there is a Novikov criterion that has to be followed, and which says that basically that the quadratic variation is finite. Now, now let's go back to our own Langevin dynamics. So, Langevin dynamics of a colloidal particle, we have written it in the differential form, and we can also, this is the first one is the forward trajectory, and accordingly you can also calculate the reverse trajectory for the reverse dynamics. Now, just by here what we will do is that we are just going to see that same Girsanov theorem, where we had two different stochastic processes that we were talking about. Here our two stochastic processes are the forward trajectory process and the reverse trajectory process, and we want to calculate what is the drift change. And so we first define the probability of the forward trajectory, that is given by the probability density of the starting position and into the conditional probability, and accordingly for the reverse the total derivative for the reverse total probability density for the reverse trajectory can also be written in the similar fashion. We also know from Sekimoto's formalism that the heat transferred to the particle can be written in this form, where this there is the quantity which contribute the viscous drag contribution and also the contribution due to the bombardment from the fluid molecules, which are which are bombarding on the particle. Now, from there we can calculate the entropy of the environmental entropy. Now, using the Girsanov theorem, we are just plugging it into that. We can see that mt equals to exponential minus xi t minus half xi t comma xi t. Now, xi t is the expression that we get for xi t is from the drift change. Now, if we use the thermodynamic interpretation and also do some mathematics, we can get that mt equals to exponential qt by t, and that is equals to exponential minus delta S environment, that is the environmental entropy. Now, if we, so we have to keep in mind that here we are talking about only the conditional probability part, which is our dp and dq in our Girsanov theorem. Now, if we want to, if we now want to go back to our total probability density, then we have PR, which is our total probability density, and PF, which is our total forward probability density for the forward trajectory. We are just multiplying that P star by PR star, that is the initial density on both the sides, and we get to this expression in the equation number 2, where we have another term which comes into the picture, which is the minus delta S system. And from there we can recover our fluctuation theorem. So, on taking the expectation on both sides, we can get back the integral fluctuation theorem. Similarly, we have also worked with the overdamped Langevin dynamics, and we have computed the drift change. Also, in case of a multiplicative noise setup, where we have sigma x diffusion and arbitrary gamma x, in that case also, since we are not restricted by what sigma or what gamma we take, so we can also calculate the fluctuation theorem for this particular setup. Now, the main key takeaways is that the Girsanov theorem brings a measure theoretic foundation to the fluctuation derivations, fluctuation theorem derivations. That is, it gives a strong theoretical foundation. Now, we see that the time reversal becomes a change of measure. We can also apply using the Girsanov theorem setup to compute the fluctuation theorem for underdamped, overdamped multiplicative noise systems. We can link the fluctuation theorem to Martingale's filtering theory, stochastic control, and many other important quantities. And it enables us to compute the fluctuation theorem for complex systems with spatial and temporal heterogeneity. So, this is a paper which has been published in Journal of Physics A. Thank you, everyone.
So, you demonstrated this for specific systems, right? A couple of specific
systems.
Yes,
we have demonstrated for overdamped multiplicative noise.
In general, this is not known, this connection between these two theorems?
No. And basically, this opens up all the different other theorems which are connected to the Girsanov theorem. All those theorems can also be used in our fluctuation theorem setup too.
Do you think it's generalizable to like in generality, more general?
Yes, it's general. We are not considering any kind of restriction on the drift and the viscous drag. Yes.
I have a question, like your fluctuation theorem is connected to the martingales, right?
Yes.
So could you please explain how it is martingale, how is it martingale?
So basically this dq by dp equals to mt, this exponential, this is a martingale, exponential martingale.
My question is explicitly, could you please explain how it is martingale?
Martingale, it means that like if you know the system from 0 to t time, you cannot predict at a later time. We cannot predict the system.
Based on the
later.
present only we can.
Yeah, yeah. And so if
What
you,
is your adaptation with respect to the measure, probabilistic measure?
yes,
What is your adaptation in this case?
adaptation meaning
Means the past.
past. Okay, so I have taken the etho picture, not the Stratonovich picture. That is, I know.
You have considered explicitly
Yes.
Ornstein-Uhlenbeck process.
Yes, yes. Yes. Yeah.
The deterministic.
Yes, for any process in general, if you have, you will have a drift term and you have a diffusion term. Yes, for any process. Yeah.
That I didn't quite understand. Like,
Okay.
anyway,
Yeah.
I'll figure it out.
My question is something related to what Kavita has just asked. Isn't it possible to derive this fluctuation theorem using within just the path integral action formulation without referring to Girsanov? Particularly for, if you even go to the discrete Markov
Yes.
chains, you don't need even path integral. You can just, fluctuation theorem almost comes automatically.
Yes, but when whenever you have those, like you have to compute from the Fokker-Planck equation. If you
No, I would just start with the Langevin, go to the path integral and say
path
property
integral,
of
yes,
the action.
I had read that paper. But I think for nonlinear cases, and it will not be that easy because there are some assumptions that has to be taken when you are doing that path integral approach. Like in,
Should be from path integral because you know that stochastic process shape must be from the path integral. Yes, of course it is possible. You are considering a stochastic process. It could be random or it could be driven. So she is considering the Ornstein-Uhlenbeck process. There must be a connection to the discrete part of it.
thank you.
So I think another relevant extension to what the discussion has been going on, and my personal question is, these forward and backward directions which you are taking to stochastic process, can they be directly related to the closed time path formalism, which is usually done for the quantum systems? There is no, per se, no reason why closed time path should be related only to quantum systems, though there is no classical analog of the same. So can you comment on that? If you are acquainted with the closed time path influence functional methods in the quantum open systems,
Sorry,
can you relate the mathematics of this to the classic, like forward and backward things which you have shown here?
yeah,
They're related.
so I'm not aware of it, but I will look into it.
Yeah, that's an interesting direction to explore. And this is a hot topic where people are trying to do it for classical systems because quantum systems is easier to do with a closed time path formalism. So this may be relevant there, which is also my personal interest. Thank you.